When your program runs, the CPU doesn't understand functions. It doesn't understand classes. It doesn't understand threads. It understands one thing: instructions. Every piece of software, no matter how complex, is reduced to a stream of machine instructions. But here's the deeper question. How does the CPU know which instruction to execute next? How does it move from one instruction to another? How does it jump, branch, call functions, return, switch threads, or handle interrupts? The answer lies in something called instruction dispatch, and today we're going to break down exactly what instruction dispatch is, how it works at the CPU level, how it relates to execution flow, how it interacts with processes and threads, and why it's one of the most fundamental mechanisms in all of computer science. Let's start simple. Instruction dispatch is the process by which the CPU selects and executes the next instruction in a program. That's it, at a high level. But that simple sentence hides a lot of depth, because selecting the next instruction is not random. It follows strict rules defined by the processor architecture. At the core of instruction dispatch is something called the instruction pointer. Sometimes it's called the program counter. This is a special CPU register. Its job is simple. It holds the memory address of the next instruction to execute. When a program begins, the operating system sets the instruction pointer to the program's entry point. From that moment on, execution becomes a cycle. The CPU reads the instruction at the address stored in the instruction pointer. It decodes the instruction. It executes the instruction. Then it updates the instruction pointer to point to the next instruction. That cycle repeats billions of times per second. This cycle is often described as fetch, decode, execute. But here's where instruction dispatch becomes interesting. After an instruction executes, how does the CPU know where to go next? In the simplest case, instructions are laid out sequentially in memory. So if one instruction is at address 1000, the next instruction might be at address 1004. The CPU simply increments the instruction pointer by the size of the instruction. That's sequential dispatch. But software is not just a straight line. Programs branch. They loop, they call functions, they handle exceptions, they switch threads. And all of that changes how instruction dispatch works. Let's talk about branching. Suppose the CPU executes a conditional instruction like, if x is greater than 0, jump to another address. When that branch instruction executes, it doesn't just increment the instruction pointer. Instead, it replaces the instruction pointer with a new address. That new address might be far away in memory. That is non-sequential dispatch. So, instruction dispatch is not just go to the next instruction. It's determine the correct next instruction based on the current instruction's behavior. Function calls are another example. When a function is called, the CPU must save the return address somewhere, usually on the stack. Then update the instruction pointer to the function's starting address. When the function returns, the CPU retrieves the saved return address and restores the instruction pointer. That's dispatch across call boundaries. Now let's zoom out slightly. Instruction dispatch is happening inside a process. Each process has its own virtual memory space. Each thread inside that process has its own instruction pointer and stack. That's important, because dispatch is not global, it's per thread. If a process has multiple threads, each thread has its own execution context. That context includes registers, stack pointer, instruction pointer. So instruction dispatch operates independently within each thread. Now let's introduce something even more important: context switching. The CPU can only execute one instruction at a time per core. But your system may have hundreds of threads. So how does that work? The operating system scheduler periodically interrupts execution. It saves the current thread's execution context. That includes the instruction pointer. Then it loads the execution context of another thread, including its instruction pointer. And then execution continues from wherever that thread left off. From the CPU's perspective, instruction dispatch never stopped. It simply resumed from a different instruction pointer. That's how multitasking is implemented. Dispatch continues, but for a different execution context. Now let's go deeper into the hardware side. Modern CPUs are far more complex than the simple fetch, decode, execute loop suggests. They use techniques like pipelining. out-of-order execution, branch prediction, instruction prefetching. All of these affect instruction dispatch. For example, branch prediction attempts to guess which instruction will be executed next before the branch is fully resolved. If the CPU predicts correctly, execution continues smoothly. If it predicts incorrectly, it must discard speculative work and correct the instruction pointer. That costs time. This is why branch-heavy code can sometimes be slower. Instruction dispatch efficiency directly affects performance. Now let's connect this back to software design. When you write code, you don't think in terms of instruction dispatch, but the CPU does. Every loop you write is implemented as a branch. Every function call becomes a jump and return. Every exception handler changes control flow. So, performance-sensitive systems often consider how dispatch behaves. For example, tight loops with predictable branches perform better. Deeply nested unpredictable branches perform worse. Virtual function calls introduce indirect jumps which are harder to predict. That affects dispatch efficiency. Now let's clarify something important. Instruction dispatch is not the same as scheduling. Scheduling decides which thread runs. Instruction dispatch decides which instruction runs next within the current thread. Scheduling operates at the operating system level. Dispatch operates at the CPU execution level. They interact, but they are different mechanisms. Now consider managed runtimes. In a runtime like the JVM, bytecode instructions are interpreted or compiled just in time into machine code. There is still instruction dispatch, but sometimes it happens at two levels. The interpreter may have a dispatch loop that reads bytecode instructions and decides which handler function to execute. That's software-level instruction dispatch. Then the CPU performs hardware-level instruction dispatch for the machine code that implements the interpreter. So in virtual machines, dispatch can exist in layers. Now let's consider something subtle: interrupts. When hardware devices need attention, like a timer or network interface, they trigger interrupts. An interrupt causes the CPU to pause the current instruction stream. It saves the current execution context. It loads an interrupt handler address into the instruction pointer. Then it begins executing interrupt handler code. After the handler finishes, the CPU restores the original instruction pointer and resumes execution. From the perspective of dispatch, the instruction stream was temporarily redirected. But dispatch itself never stops. It simply switches to a new control flow. Now let's summarize the key components involved in instruction dispatch. The instruction pointer holds the address of the next instruction. The current instruction determines how the instruction pointer is updated. Branches and jumps modify the instruction pointer. Function calls save and restore return addresses. Threads maintain independent instruction pointers. Context switches save and restore instruction pointers. Interrupts temporarily override instruction flow, and modern CPUs use prediction and speculation to optimize dispatch. At the lowest level, software execution is nothing more than repeated instruction dispatch. Everything else, processes, threads, frameworks, runtimes, applications, is built on top of that simple cycle. Fetch, decode, execute, update instruction pointer, repeat, billions of times per second. Now let's correct a few misconceptions. First misconception: the CPU runs functions. It does not. It executes instructions sequentially or via controlled jumps. Functions are just patterns of instructions and control flow. Second misconception: the operating system controls every instruction. It does not. The operating system controls scheduling and interrupts. But dispatch inside a running thread is handled by the CPU itself. Third misconception: threads run simultaneously inside one core. They do not. One core dispatches one instruction stream at a time. Multi-threading relies on context switching and multiple cores. Fourth misconception: instruction dispatch is simple and constant cost. It is not. Branch prediction, cache locality, pipeline depth, and speculative execution all influence dispatch efficiency. So why does instruction dispatch matter? Because it is the foundation of execution. It determines performance. It determines responsiveness. It determines how control flow behaves. It determines how concurrency feels at runtime. And it determines how your code translates into actual hardware behavior. When you understand instruction dispatch, you understand that software is not magic. It is a controlled, deterministic flow of instructions guided by a pointer. Every system you build, from a tiny embedded device to a massive distributed server, ultimately runs on this mechanism. Instruction dispatch is the heartbeat of software execution, and everything else is structure built on top of it. If you want to go deeper, the next step in this execution series could be exploring how pipelines and branch prediction affect performance, or how interpreters implement dispatch loops at the runtime level. But for now, you can reduce software execution to one essential truth. The CPU repeatedly selects the next instruction and executes it. That selection process is instruction dispatch, and that is how all software runs.